Hi everyone, welcome to machine learning. Uh, the, this is session number 3, part 1. This is dealing with probability and distributions and hypothesis testing. It is part of the ML using machine learning using Python, and three uh, classes were conducted. That is module 1 and module 2. Uh, Module 2 had part 2, which was completed. Module 2, part 2 was completed last uh, Friday. This is every Monday, Wednesday, Friday. This being the fourth class, uh, I, I have found interesting that Saurabh has been really following thorough and Jaymeet has been very much on top of it. And we look forward to really good association going forward. And I will give it the handle to Jaymeet Osawa, who has been putting all effort to make sure that this ML using Python is successful. So this is the fourth out of 24th because this is 2 months course and we are just at the beginning. So hopefully Janet will be able to satisfy everybody who has been attending or not attending but viewing through the records. Go ahead, Jaymeet. Congratulations. Go ahead and take forward.
Yeah, thank you, sir. So, hello everyone. Uh, Welcome to this module where we'll be discussing about probability distributions and hypothesis testing. So, this module is divided into two parts, as you can see, 3.1 and 3.2. Today we'll be going with 3.1, which is probability distributions. The previous one was descriptive analytics. We discussed about the matplotlib and cpon as libraries and how the past data can be used in order to gain the insights of what happened. Now we'll be discussing about the probability distributions. So the learning objective for this session will be to learn the different concepts or introductory concepts of the probabilities, such as a random variable, then a sample space, a random experiment and stuff. Then we'll be also discussing about different type of distributions, such as a normal distribution or Gaussian distribution, exponential distribution, Poisson distribution, binomial distribution will be the first one that we'll be discussing. Then the last one, as it says, learning how to derive insights from statistical measures such as mean, variance, probability distribution functions, confidence interval, etc. So let's start with getting used to some of the terms that are used in probability theory. So some of the terminologies that are used and what they mean. So when do we use probability? We use it in order to see the uh, number of outcomes that can come in our favor, or whether it can be uh, from many choices, like a dice. It has 6 sides, so how many can come in our favor? Let's say 6 is the favored one, so one of 6 possibilities are there. The same goes for head and tails, as a lot of time, as in every game of cricket, a coin is tossed, and depending on who won the toss, they calls for which side of the game they will be playing first. So, why do we use probability and its application? So, probability of occurrence of an event. So here, as in the coins example, we had the outcome of head on a coin toss with 2 outcomes. There can be only 2 outcomes, whether it's a head or a tail. Then to test the hypothesis. Hypothesis basically means that what do from our past understanding of things, we have a current belief. So if it's a cloud, if it's a cloudy weather, it's going to rain. So that kind of thing, because we are always seen a cloudy weather whenever it rains, we our current hypothesis means that because it's cloudy, it's going to rain. Then building models to explain variation in key performance indicator, which is for the business importance of understanding the profitability, the market share, demand, etc. Probabilities also help us understand uh, which are the key performance indicators. Uh, while building models, there are certain features that impact the result of the models, which which makes the difference in our understanding and gives us insight about which are the factors that give us more profitability. And it can be in terms of shares or certain kind of investment or supply and demand and stuff, if we talk about a whole scenario of the business. So the first term will be called as a random experiment, which is the output of the uh, random experiment is something is an output where the output cannot be predicted, but once performed, we know the output of it. Now, there can be certain kinds of output only. So in the previous example, we talked about the heads and tails. So heads and tails are the only output that can happen in the sample space. So these kind of space, or you can imagine a set for a second, and a set containing every output that is possible. So that is what we will call a sample space. A sample space contains every kind of possible outcome for an experiment. So a sample space is represented by S, and an individual outcome are called elementary events. A sample space can be finite for in terms of heads and tails, or dice, or an infinite real numbers between 1 to 9, and so on. So let's understand with some examples. So let's say our experiment is an outcome of a college application. So the sample space will will be having the possible outcomes of submitting an application to the college. What can be the outcome of the samples? What can be the what kind of outcomes can there be in the sample space? Whether an application can be accepted or admitted, or rejected or not admitted. The same kind of scenario is in churn prediction. So whether a person stops using a person's a business's product, or it continues with the use. Then comes for television rating point. Now television rating point is not showing a particular scenario, a countable scenario, but it's rather showing us a range within which something can be present. So our television rating point can be present from 0 to 100%. Next is an event, which is a subset of a sample space, and probability is usually calculated with respect to an event. So For example, an event can be number of cancellation of orders placed at an e-commerce portal site exceeding 10%. Then the number of fraudulent credit card transactions exceeding 1%. The life of capital equipment being less than 1 year. Number of warranty claims less than 10, or a vehicle manufacturer with a fleet of 2,000 vehicles under warranty. So let's just take few examples for for the terms random experiment, sample space, and events together. So first is a dice. One dice is being rolled. What would be the probability of it being rolled to 6 being up? So the sample space will contain all the probabilities, or sorry, all the outcomes that can be possible. So a dice has 6 sides. So all the 6 outcomes are there. What we need for an event is that the dice should be the dice with 6 should be facing up. So there is only one event that is present from that sample space. So the probability is 1 by 6. Then in the next example, in an example of in an exam of 100 marks, what is the probability of students scoring more than 60? So here the random experiment is exam. The sample space is our marks from 1 to 100, and the event is a student scoring more than 60 marks. Next is, sorry.
What is n of A and n of B? So I couldn't get that. N of S or n of A?
So n of s is nothing but the, so say, 6 is just showing that 6 side up is the one. So 6 is not representing 6 as a number, but 6 is representing the dice's side of 6 being up. So 6 is not a number, but a representation of the event. And n of A means that there is only one possibility out of the sample space that there can be the 6 can be up on the dice.
Okay.
Yeah. Next is random variable. So random variable is a function that maps every outcome in the sample space to a real number. So just as we just discussed about it, so 6 is not a number here, but 6 is an outcome that is being represented by the dice's side of 6 being up. So that is how random variables are used, and they represent an outcome from the sample space. So a random variable is a function that maps every outcome in the sample space to a real number, plays an important role in describing, measuring, and analyzing uncertain events such as customer churn, employee attrition, demand for a product, and so on. If the random variable, which will be always denoting with x, or to be really specific, capital X, so x can assume only a finite or countably finite set of values, then it is called a discrete random variable. So let's say credit card rating. So usually classified into different categories such as low, medium, high, or using labels such as AAA, AA, A, triple B, etc. Then comes the number of orders received at an e-commerce retailer, which can be countably finite. The customer churn, whether they stop using your product or continue with the usage. Then comes fraudulent transactions, whether they are fraudulent transaction or they are genuine transaction.
Okay, so what is the difference between only finite or countably infinite? So both are finite, right?
Yes, in a way, yeah. So so for countably, so for infinite things, let's say and there are numbers, real numbers between 1 to 9, as we also said. So it can be 1.99, it can be 1.9999, and so on. So there can be many values between 1 to 9, infinite in a way. But in countably infinite, it means that, let's say, the values are keep on adding, and a certain kind of values fall within a certain range. Are you so just a second. So you are talking about the bullet point, right? If the random variable x can assume only a finite or
Yes.
a countably infinite set of values.
Yeah.
So
Yes.
here it can just for the time, just understand that, and this time the value of x will take a specific value. It will be appointed as a specific value, for, let's say, it can be 1.99 or 9.99 or anything, but it will be a specific x value, because
Okay.
there will be a different uh, further when we discuss about in this session, you will get it clear why we are saying this finite and countably infinite. So a random variable which can take a value from a infinite set of values is called a continuous random variable. Now when we say this, that here we are also saying that countably infinite set, or we are saying here that it can take a value of set of infinite values over here also for continuous random variable. But when we talk about continuous random variable and differ it with a discrete random variable, when we are talking about continuous random variable, we are talking it about within a specific range. So a random variable x, which can take a value from an infinite set of values within a specific range, is called as continuous random variable. So for example, market share of a company, which can take any value from an infinite set of values between 0 and 100%. Then percentage of attrition employees of an for an organization, time to failure of an engineering system. So let's say a rod made up of a certain kind of metal will withstand certain kind of pressure. So that's what it says, time to failure for an engineering system. It can be for anything, not just a rod, but for a construction of a building and so on. Then comes time taken to complete an order placed at an e-commerce website. Even though there can be certain kind of values, let's say uh, to from a customer buying a product to just a confirmation that the person has bought the product, it takes 20 seconds. But that within those 20 seconds, there can be infinite values that can be taken in. So within that specific range of uh, time being below 20 seconds are the infinite set of values that a continuous random variable for the scenario of order placed at an e-commerce portal can be counted. So we talked about discrete random variable first, where a random variable will take a specific value. So this discrete discrete random variable, they are described using two types called probability mass function PMF and cumulative distribution function CDF. So first, probability mass function is the probability that the random variable x takes a specific value k. For example, the number of fraudulent transactions at an e-commerce platform is 10, will be written as p of x equals to 10. Then for the cumulative distribution function, the probability that a random variable x takes a value less than or equal to 10. See, there comes an age now, a range now. So it will be written as p of x smaller than or equal to 10. So some of the examples for discrete random variables, the same as before, credit card ratings can be low, medium, high, or AAA, A, and stuff. Then comes number of orders received. It can be anything in crores and stuff. Then comes the customer churn. As written, it will take a binary value, whether it will stop or so. You can also represent it by 1 and 0. Then comes the fraudulent transactions. So for the PMF or a probability mass function, let's take an example for heads and tails being being flipped 3 times in a row. And uh, what will be the output for it? What are the possible outputs to it? So our sample space contains the possible outputs when we flip a coin 3 times in a row, and what are the outcomes that we get for it. So our random variable is number of ways heads can result while tossing a coin. So any time or the any time an outcome contains heads, that is what we want. So how will we represent that x? So if x equals to 1, or so from x equals to 0 to x equals to 3, it x equals to 0 means no heads are in the outcome. Then comes one number of times that head is only one time out of the three flips. Then comes 2 times that head are in the place of outcome, and x equals to 3 for 3 heads turning out. So if this description confuses you, let's go through the P of x equals to 0 first. So what is P of x equals to 0? That there are no heads out of the 3 flips of coin that we have done. When will it happen? It will happen when 3 times the result was tails. So we, out of the 8 outcomes that we have, 1 by 8 is the probability of it. Then the same, what is x equals to 1? It was the number of outcomes where head is equals to 1, or the head turns out to be 1 time. So it's 3 by 8. And you can see the order for STT, THT and stuff. The same goes for x equals to 2, that 2 heads are in the outcome and then 3 heads in the outcome. So you can see the probability of those events occurring. Now let's take the same kind of yeah, a discussion like rolling a dice or flipping a coin. So this time we'll be talking about rolling a dice, and we'll be seeing the probability that the outcome is less than or equal to 3. So the value on the dice should be less than or equal to 3 for all the independent trials. So if you roll, for the first one, if you roll a dice and 1 appears, the probability of getting a value less than or equal to 1 is 1 by 6 out of the 6 sides. Then comes for 2, the probability is 2 by 6, as there are 2 outcomes. It can be 1 or either 2. The same for 3, the probability of getting a value less than or equal to 3 is 3 by 6, and there can be value 1, 2 or 3. So we even if we discuss about all the roles of 4, 5 and 6, you get the picture that what we are talking about. So the cumulative distribution function gives you the cumulative probability to a certain value, like adding all the probabilities of getting values less than or equal to that specific value. So in this cumulative distribution function, we talked about getting a value on the dice less than or equal to 3. Now, about the continuous random variable. Till now, we were discussing about the discrete random variable. So a random variable x, which can take a value from an infinite set of values, is called a continuous random variable. So the same examples, market share of a company, percentage of attrition of employees, time to failure of an engineering system, whether it can be construction, simple rod or anything. Then time taken to complete an order placed at an e-commerce portal. So when we try to describe these continuous random variables in a mathematical form, so just like the discrete random variable was described using probability mass function and cumulative distributive function, the continuous random variable also is used or also is described using probability density function. First, in discrete, we had probability mass function. Here we have probability density function. So, so when we mathematically represent the probability density function, which is PDF, then we get this expression which reads f of x equals to limit delta x tends to 0 delta p sorry limit p delta x tends to 0, and the x's value lies, or the random variables value lies between the x smaller than uh, the random variables, which is denoted by capital X. Its value lies between x and x plus delta x. So it's a very small uh, space, or uh, in mathematical term we call it value in small neighborhood of x. Then the same thing, if we try to mathematically represent the cumulative distribution function, f of a equals to integration minus infinity to a f of x dx. So the random variable takes value less than or equal to a value of a. So negative infinity just takes care of all the values it can take till the value of a. So with the moving further with the probability density function, imagine you have a continuous random variable like the height of people in the population. The probability density function tells you that relative likelihood of a random variable falling within a specific range of values. So we are taking, let's say, a height of certain population. So the PDF, or the probability density at height of 170 centimeter from the population, or from the values that we have gathered at height 170 centimeter, the probability density's value is 0.02. It means that the likelihood of randomly selecting an individual with a height very close to 170 centimeter from this population is 0.02 per unit of height. So if we randomly select someone from a population of our uh, from which we have gathered the data, the probability, there is a probability that the adult will have the height of or near 170 centimeter. So it kind of gives us a confidence regarding a specific range of values that our reading will fall around. So going with the heights example, but for a different topic, which is cumulative distribution function. So for a CDF f of x at a specific height x gives the probability that a randomly selected individual from this population has a height less than or equal to x. So as from 160 to 190, we have different kind of height readings, and having the height less than 170, there are total 3 readings that we have from the total 7 values that we are taking from. So f of 170 is equal to 3 by 7. So regarding the representation, that it's similar to what we discussed for the CDF in the continuous random variable, that f of x equals to p of capital X smaller than equal to x for this representation. So for a discrete random variable, the cumulative density cumulative distribution function is evaluated at each possible value of the random variable, whereas in continuous random variable, the cumulative distribution function can be evaluated at any point within a range of possible values of the random variable. So after knowing some of the terminology and the distributions regarding the probability, let's discuss some of the common distributions that are used. First is a binomial distribution. Binomial distribution is nothing but a distribution where the outcome leads to whether success or failure. So a random variable x is said to follow a binomial distribution when the random variable can have only two outcomes, success and failure, which is also known as Bernoulli's trials. The objective is to find the probability of getting X successes out of N trials. The probability of success is P, and thus the probability of failure is 1 minus P. The probability P is constant and does not change between the trials. So the same examples that we have been taking, the customer churn, the fraudulent insurance, and then the loan payment, whether the customer will default or not default. Just a second. So for the binomial distribution, so for the binomial distribution, we have we are taking an example of uh, an e-commerce company that sells women's apparel, and it is observed that 10% of their customers return the items purchased by them for their return for any kind of reason on a specific day. So we are taking an example for a specific day. So on a specific day, 20 customers purchased items from FTO, which is Fashion Trends Online. So we'll be calculating the probability. Exactly 5 customers will return the items. Then probability of that maximum of 5 customers will return the items. The probability that more than 5 customers can return the items purchased by them, and the average number of customers who are likely to return the items, and the variance and the standard deviation of the returns. So first, we'll be importing, we'll be using stats, which will give us the binomial model for it for calculating the probability mass function. So the stats.binom .pmf is the method that will be using for calculating the probability mass function for the binomial distribution that we have, which takes three parameters, which are expected number of successful trials. Here we have 5, the total number of trials 20, and the probability of success, which is zero point 0.1 or 10% here. So when we use stats.binom.pmf to calculate the the probability mass function, we get the value of 0.03. So the probability that exactly 5 customers will return the item is approximately 3% for the values that we have put in. For number of trials 20 and the probability of success 0.1. Then we are also going to visualize certain things. So we'll be using the pandas, matplotlib and seaborn. So first we'll be creating a data frame called pmf for probability mass function df. From there we'll be creating the success range and specify the range for it, 0 to 21 for 0 to 20, and for the PMF values we'll be going for the range as well from 0 to 21 for its PMF values. And then give the same values for 20 for number of trials and 0.1 or 10% for the success rate. And then we'll be using the Seaborn's bar plot for plotting bar plot. Give the X values for the DF that we have used, and within that we'll be using success for our X values and the PMF values on the y-axis. So this is the graph that we get, and you can see that number of items returned for 20 trials that we are taking and the PMF values that are there. So you can see that the PMF values for 2 items being returned are the most, which is more than 25%. But as the number of orders or items increases, the probability kind of goes down. Then the next thing that we were going to calculate was a probability that a maximum of 5 customers will return the items. So so here we'll be using the binom.cdf for cumulative distribution function. Give the same values, and the corresponding probability value for CDF that we get is 0.9887. The next thing that we'll be calculating was probability that more than 5 customers will return the items purchased by them. So in order to calculate that, we can simply deduct the value that we have calculated here for CDS and minus it with one. So we'll be simply using 1 minus 1 denoting all the probabilities. So deducting the values for maximum of 5 customers will get the probability that more than 5 customers will return the purchase value for them. So as you can see that we get the value of 0.0112. The last one was about mean and variance. So the average number of customers who are likely to return the items and the variance and the standard deviation of the number of returns. So the average of the binomial distribution is given by n into p, and the variance of binomial distribution is given by n into p into 1 minus p. So for the values that we are calculating, we get the average value of 2 and the variance of 1.8. So on an average, there are two items that are returned, and the stand the variance we have is 1.8. So this is nothing but the code that was used for the plotting of graph. So the probability mass function of the binomial distribution, probability that the number of success will be exactly x out of n trials, was given by this. So n over x into p of p raised to x into 1 minus p whole raised to n minus x. Or you can also go for n factorial by x factor x factorial into n minus x whole factorial. The same goes for a cumulative distribution function for the binomial distribution. So probability that the number of success will be x or less than x out of n trials will be given by summation of n choose k into p raised to k into 1 minus p whole raised to n minus k. So as you know that we have used SciPy's stats model, and from that we use its binomial model to work with. The next in discussion is a Poisson distribution. So when is Poisson distribution used? Like in binomial distribution, there were two outcomes. So that's why we used a binomial distribution. And Poisson distribution is used when we want to express the probability of a given number of events occurring in a fixed interval of time if these events occur with a known constant mean rate and independently of the time since the last event. So let's say there is a certain kind of event is occurring, and it is occurring at a constant or at a certain rate, and the occurrence of one event is independent of occurrence whenever previously it has happened. So there are examples for Poisson distribution are number of printing mistakes for the page, days on checks at the bank, cancellation of orders by customers at an e-commerce portal, then customer complaints, cash withdrawals at an ATM, typographical errors in a book, potholes or on roads, etc. These are the kind of these are the examples for Poisson distribution. When we mathematically want to present this, so P of x equals to k is given by e raised to n e raised to minus lambda into lambda raised to k by k factorial, where lambda is nothing but the rate of occurrence of the events per unit of measurement. Generally, it is and the unit of measurement is time, but it is not necessary. So, so now we'll be discussing about a scenario, just like last time we discussed about uh, online e-commerce platform and the items returned by the customers. And this time we'll be discussing about a call center which follows a Poisson distribution at 10 calls per hour. So we'll be plotting this graph as well there. So in many situations, we may be interested in calculating the number of events that may occur over a period of time or space. To find the probability of a number of events, we use Poisson distribution. So for the example of a Poisson distribution, we will be taking an example of a call center where the number of calls arriving at a call center follows a Poisson distribution at 10 calls per hour. So first, we'll be calculating the probability that a maximum of 5 calls will arrive at the call center. As the number of calls arriving at the call center follows Poisson distribution, we can use stats Poisson.ctf to calculate the probability value. It takes the following two parameters. The first parameter is number of events. Here we are taking the scenario of maximum of 5 calls that will arrive at the call center, for which the probability needs to be calculated. And the second parameter is the average number of events, which for the call center in scenario is 10 calls per hour. So after using the model for our Poisson distribution, the and giving the parameter values for 5, the first parameter is a number of events for which the probability needs to be calculated, and the second is the average number of events that occur, so 5 and 10, and we get the value of Poisson CDF is a 0.067. The next is the next thing that we'll be calculating for the scenario that we are discussing is calculate the probability that the number of calls over a 3-hour period will exceed 30. So since the average calls per hour is 10, so the rate or the lambda value is 10, and we are interested in finding calls over 3 hours. So the mean number of calls over 3 hours at lambda t is 30. So we we calculate it by 1 minus stats Poisson dot cdf and giving the value of 30 first for the number of events that it can occur. So for us, it's 30 calls, and then over the time of 3 hours for the rate of 10. So 3 into 10, 30. And we get the probability value of 0.45, that there is a 45% chance so that the over the 3 hour period, the calls will exceed, the number of calls will exceed the mark of 30. So this is the plot for the number of calls received and the time. So yeah, just a second. The next we'll be discussing is exponential distribution. So it is often concerned with the amount of time until a specific event occurs. So let's say for earthquake is the most common example when we talk about exponential distribution. So the time before a certain event happened, the last time the earthquake happened, and the time between the next earthquake might happen. So traditionally used for modeling time to failure of electronic components, the exponential distribution represents a process in which events occur continuously and independently at a constant average rate. So amount of time until an earthquake occurs has an exponential distribution. Then comes a duration in minutes of long distance business telephone calls. The duration of the business telephone calls. Then the amount of time a car battery lasts. So these are the kind of events where the exponential distribution is used. So or until a certain event occurs, or until a certain specific event occurs. So the exponential distribution is widely used in the field of reliability or reliability tests, reliability dealing with the amount of time a product lasts. So the probability mass function of exponential distribution exponential distribution is given by formula f of x equals to lambda e raised to minus lambda x, where x's value will be greater than or equal to 0. This is the mathematical representation to it, where lambda is nothing but the rate of occurrence of the event. Then mean of exponential distribution is given by 1 by lambda. So here again, we'll just like we have been taking different scenarios in order to understand different topics, we'll be discussing about uh, a, a failure rate of an equipment. So we'll be discussing about time to failure of an avionic system follows an exponential distribution with a mean time between failures, which is also called as MTBF, mean time between failures of 1000 hours. So this will be the plot that we'll be taking, and in a um, briefly speaking, this is showing the reliability as a number of hours passes for the for equipment as an example. So here it is the avionic system. So the time to failure, you can see that it decreases. So for this, we'll be calculating different uh, we'll be calculating something probabilities based on different scenarios. So the example for exponential distribution, the time to failure of an avionic system follows an exponential distribution with a mean time between failures MTBF of 1000 hours. So calculate the probability that the system will fail before 1000 hours. So calculating the probability of the system failing before 1000 hours will be using the expon, which denotes to the stats model of exponential distribution, and we'll be going for the cumulative distribution up to a value of 1000. For a exponential distribution will give the probability that the system will fail before 1000 hours. So 1000 is the value. Now just a second. Now log value, which is the mean value, remember that this is so 1 by 1000 at the scale of 1000. So when we go for calculating the exponential distribution, we get the probability of 0.6321. Just a second. So there is a probability of 0.63 before the avionic system uh, can fail before the 1000-hour mark. The next scenario that we'll be calculating is calculate the probability that it will not fail up to 2000 hours. As you can see that it says not up to 2000 hours. We have to simply get the values of 2000 over here for the log and the scale value of 1000 and deduct it from 1. So we get the value of 0.13. So we are simply we are getting the value of 0.13 or the probability of 0.13 that the avionic system will not fail up to 2000 hours there. The the third thing that we'll be calculating is a calculate the time by which 10% of the system will fail. So this as this is a percentage value, the first parameter will be taken is in that form. So it will be 1.1 or denoted by 0.1. So this can be calculated by PPF or a percent point function, and it is an inverse of CDF. So stat model of exponential distribution gives us the PPF or the percent point function that takes the percent point value and the mean and the scale of the exponential distribution. So we are
Jaymeet,
yeah.
uh, what time you will be closing?
Uh, right now, I have certain topics to cover now.
I'm just checking because 8 o'clock we have another one. So uh, you are
The,
not going to cover the other one, right? Second one.
no, no, there is a different part, but I have
No.
the
No. So
so
yeah. Okay. So you have got few slides to complete, right? See if you can complete by 8:15. Okay.
okay, okay,
Because we have another one to start at 8. So just in case.
okay,
Okay.
okay,
No problem. No
yeah,
problem. So you skip the other part. Take it on part 2.
okay, no, no worries. I'll
Yeah. Go ahead.
yeah,
Go ahead, sir.
let's just see. So so for this for calculating this calculate the time by which 10% of the system will fail. We are we have 105.36 hours that 10% of the system will fail. For the visualization of the exponential distribution by plotting the PDF function against different time to failure hours. So what we are doing is ranging the success for from 0 to 5,000 hours and giving it a step of 100. The same for the mean value as well as the scale as we have used over here, the values that we have used over here. Sorry, not here, but here. And then plotting the figure using the Seaborn's bar plot over here, giving the x-axis value of PMF DF success and the PMF values of the PMF DF. So you can see that as time passes or as the number of hours grows, you can see that the value decreases. Next, we will be discussing is a normal distribution. So which is also known as Gaussian distribution. So a function, it represents a function that the distribution of many random variables is a symmetrical bell-shaped curve. And because of that bell shape, it is also called as a bell curve. So the normal distribution is observed across many naturally occurring measures such as age, salary, sales, volume, then birth weight, height, etc. So as said, it is popularly known as bell curve. So for understanding the normal distribution, we will be taking a scenario for two stocks in a that were listed for on that were listed on Bombay Stock Exchange. The first one is a BEML, and the other one is Glaxo. So we'll be only using the open and close price of these stocks for calculating and discussing the scenario. And this is the plot that we'll be doing for using the gain on the respective stocks. For you can either use a disk plot, which will be a discontinued feature in Seaborn, or you can use the HISC plot here. Now let's discuss the normal distribution. So using the data sets for the prices of both BEML and Glaxo as the stocks, we read the file for BEML, and for Glaxo we are reading the file, and you can see this sample, the same for BEML. So as also mentioned, that we are interested in the date and the closing price at the end of the day, that or the at the end of the date that these two stocks had. So we'll be creating the data frame regarding that. So for BEML and Glaxo, the respective data frames, and create it. So first we are using the sample of for Glaxo and the date as well as its closing price on that respective date. Then plotting the values for Glaxo for the time and the close price, and you can see that there was a and it started from the bottom, and then it rise and then dipped at 2012, again showed a rise in mid 2013 and 14, then dropped, then again is rising, and in the end for the values between 2016 and 17, it's going down. The same kind of insights can be gained by plotting the values of BEML. It showed a huge dip in 2013 to 2014, but then it rose in 2015 to 16, and it's going on for 2017. So, as discussed, we are discussing the gains that were made by the respective stocks. So what is the expected daily return? The which stocks have higher risk or volatility as far as daily returns are concerned. So what is the expected range for the return for 95% confidence interval? And which stock has higher probability of making a loss risk at daily return at 2% or more, and loss risk loss or risk of 2% or more. So this is the formula for, hello. So this is the formula for the gain, and that we'll be using the present price minus the previous day's price with we'll be seeing its value with respect to the previous day's price. So we are adding a column gain to both of them, and on their DF's close column we are using the PCT change for the period of 1. So what PCT simply does is it gives the change for the all the rows above, and as we are giving period equals to 1, so we want it for every row above it. So you can see that what we get for these values. For Glaxo, you can see that we have gain, as of course the first will not have any value, but later on we get the differences. Then you can see the gain and till 2017 for Glaxo. When we plot the graph, you can plot the graph using this for the gain. Then using the comparing both of these stocks for Glaxo as well as BML using the BEML using the histogram plot, and this is how the plot looks for comparing. So when we calculate the daily gain of Glaxo, we simply have to calculate the mean and give the value. So you can see the mean for Glaxo as well as the standard deviation. And the same goes for BEML and its standard deviation. So when we use the dot describe function on a method the on the data frame on the gain, you can see the kind of uh, values that we get, the mean and the maximum and stuff. The next thing that we'll be discussing are the mean and variance, or different used. Also known mean, also known as the average. It is calculated by adding all the numbers in the list and dividing by the uh, number of numbers. We'll go through the mean and variance in an introductory fashion, as these are some of the concepts that we are already familiar with. So median, the middle value in the list, calculated by ordering the number of smallest to largest, taking the middle number. Mode, the value that occurs most often in the list, is called a mode. Then comes the standard deviation, how much the value of the normal value of data points deviate from its mean. Or you can also say that what is the measure, it is the measure of a dispersion of the data in relation to the mean. Uh, so variance is a square of a standard deviation. So you can also connected to permutations and combinations, where for permutation, if order matters and repeats are allowed, it's n n raised to r, and where repeats are not allowed, it's n factorial by n minus r whole factorial. The same goes for combinations where repeats are allowed and not allowed. The r plus n minus 1 whole factorial by r factorial into n minus 1 factorial, and n factorial by r factorial into n minus r whole factorial for no repeats in combination. So in permutations, the order doesn't matter. In combinations, sorry, in permutations, order matters. The combinations order doesn't matter. Sorry. For calculating the standard deviation, this is the formula: the square root of summation of all values of the data minus the mean of the data whole square divided by n minus 1, and all within the square root that was mentioned. And these are two links that you can use for the reference for understanding the formulas and of the standard deviation and variance and the permutation and combination. So as the normal distribution, you can see that how it distributes and how from mean the percentage of values are distributed. So for one standard deviation minus or plus, you can see that we get 34% of coverage for minus and plus both. So having 68% for the single standard deviation. If we 2 times the standard deviation, we are covering almost 95% of the population of the data. And for 3 times the standard deviation, we are covering almost 99.7% of the data. So why do we do this? Because to find out what is expected range of a return for 95% confidence interval, which are the things that will make us have the value fall under the 95% coverage of the population's values. So we need to calculate the values of gain for 2 standard deviations away from mean on both the sides of the distribution, that is mu plus or minus 2 sigma. The probability that the parameter lies within a specified range, and 95% confidence interval for a population mean. It's just an example, as you can see, at how it covers a 95% of it. So confidence interval is a statistical measure that provides a range of estimates within which an unknown statistical parameter is likely to fall. It is calculated to a selected confidence interval, which represents the probability that the confidence interval contains the true parameter value. The confidence level indicates the reliability of the estimation of procedure and not the certainty that the specific interval contains the true value. So let's say we are throwing a ball, and the confidence interval contains x plus x, or from x to x plus 4. This is the distance within which we have the 95% as the confidence interval, but it does not give us the true value, or it does not give us the certainty that it will always fall within this value, but it gives us the 95% confidence that if we are throwing the ball, it might fall under this distance. Then comes the confidence level, which describes the uncertainty associated with confidence interval. It signifies the proportion of confidence intervals constructed at the chosen confidence level over many independent trials. that will contain the true parameter value. So confidence interval does not have the certainty of containing the true parameter value. So having a 95% confidence level implies that 95% of the out of 100 intervals constructed in the same manner would contain the population parameter. So for a confidence level and for interval, let's take an example. Which first one is a customer satisfaction survey. A company conducts a customer satisfaction survey and asks 50 randomly selected customers to rate their satisfaction on a scale of 1 to 10. The sample mean satisfaction rating is 8.2. Using a 95% confidence level, you can calculate a confidence interval for the true mean satisfaction rating of all customers, and the confidence interval might be for meaning 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 that 95% confident that the true mean satisfaction rating of all the customers lies between 7.8 to 8.6. The next example is flipping a coin, 55 heads of 100. Then we have the confidence interval of 0.45 to 0.65, confidence level of 95%. Height of students, the confidence interval might be measuring the heights of 20 randomly selected students and calculate the sample mean height as 165. So, or so 162 to 168 are the 90% confident that the true mean height of all the students lies between 162 and 168. So the interval that we will be using for the stats model or for the normal distribution, it takes three parameters, which are alpha, log, and scale. Alpha is the interval for 90% confidence interval and stuff. Log is the mean of a normal distribution, and scale is the scale parameter of the distribution, which is a standard deviation for the normal distribution. So for the gain that was used for so we were talking about the scenario of two stocks that were listed in a Bombay Stock Exchange, Glaxo and BEML. So for Glaxo, we are creating another DF for confidence interval, giving the values of 0.95, the mean, and calculating the gain standard. So when we calculate its value using this normal distributions model of stats models, then we get the gain at 95% confidence interval for our stock Glaxo is minus 0.0258 to 0.0266. The same goes for a BEML. When we calculate, we get a minus 0.0515 to 0.0521. The next thing that we'll be discussing is cumulative probability distribution, which represents the probability that the random variable takes on a value less than or equal to specified value. So cumulative probability distribution, it refers to the cumulative probabilities associated with different outcomes of a random variable. So for discrete random variables, a cumulative probability table is often used for organized outcomes and their probabilities, facilitating the calculation of cumulative probabilities for specific values or ranges. The table accumulates probabilities as the outcomes increase with the cumulative probability summing up to 1 at the end. So understanding cumulative probabilities is essential for assessing the likelihood of specific events or values occurring within a given distribution. So as discussed, this is the same mathematical representation. Having the value of x lying in a very small neighborhood of, or the values lying with a very small neighborhood of x, or neighborhood of x. To calculate the probability for gain higher than 2% or more, we need to find out what is the sum of all the probabilities that gain can take values more than 0.02. So this is regarding the questions that we are trying to solve. So these are the two things: the higher probability of making a daily return of 2% or more, and which stock has the higher probability of making a loss or risk of 2% or more. So to calculate the probability gain, hello.
Yeah, you're completing.
Yeah, just one slide more.
Yeah, sure. Thank you.
Yeah. So we have we are using Glaxo's mean and standard for the parameters it takes for the values of minus uh, 0 to minus 0.02. So probability of making 2% gain or higher in Glaxo is 0.63, and probability of making 2% gain or higher in BML is 0.22. For daily gains of Glaxo and BML, you can change the parameter values over here for the respective BML and Glaxo DF while using the argument, and while deducting them from 1. The probability that we get is for a Glaxo is 0.071 and BML for 0.2276. So this was about this session was about probability distributions, and we discussed about probabilities first, got used to certain kind of theory or terminologies that was needed while discussing probability, uh, the random experiment event sample space, then discussing different kind of common distributions. So the other few normal distributions are beta distributions, gamma distributions, Weibull distributions, and geometric distributions, having their own different uses. As geometric, which is if the binomial distribution is about how many successes, then the geometric distribution is about how many failures until a success. And so as the distribution have their own different uh, uses for the for our aim or goal or objective to be used. So this was it for the probability distribution. Thank you.
Yeah, I think Jaymeet,
Yeah.
Any questions from Saurabh? Are you, okay? Looks like he's dropped out.
Yeah.
Okay, so what we do is I will thank you very much for the presentation. We'll post the recording after this call, maybe by in the night, midnight, and hopefully follow up on the uh, subject matter as part two of it, which we will cover the rest of the related to the hypothesis testing and all. Okay,
Yeah.
thanks a lot, Jaymeet, and take care. Bye
Yeah.
for
Thanks.
the day.
Bye.
Yeah.